Hi, my name is Ava Prakash. In this series of videos, I'm going to talk about the interpretation of nonlinear gapped-Kamer support vector machines using integrated gradients. I'll explain the key intuitions of the paper shown below. So in this particular video, I'll cover the key background concepts needed to understand the ideas of the paper. The main motivation of this paper is to have an efficient way to classify and interpret genomic sequences associated with disease, and therefore identify the important transcription factor binding motifs in the classified sequences. The key challenge here, and the contribution of the paper, is the algorithm for attributing the classifier's decision to each individual base pair of the input sequence. These attributions, or importance scores, then enable us to identify binding motifs in the sequence. The classifier we have in mind here is support vector machines, or SVMs, and in this video I'll assume a basic familiarity with machine learning concepts, specifically SVMs, and also familiarity with basic genomics concepts, like sequences, transcription factors, and binding motifs. So first, I'll talk about the SVM decision function, because it is the value of the decision function that we're really interested in attributing to the individual base pairs of an input sequence. Next, I'll cover the kernels commonly used for SVMs to specifically classify genomic sequences, and also how they are efficiently evaluated. Lastly, I'll explain the integrated gradients algorithm for decision function attribution. In the next video, we will get into the development and application of that algorithm to SVMs for genomic sequences. So in this slide, I'll talk about the decision function of SVMs. As we show in the diagram on the left-hand side, an SVM essentially takes a set of input examples, the blue and orange dots, and classifies them as either positive or negative. Here we have the blue as positive, labeled with yi as +1, and orange as negative, labeled with yi as -1. The decision function boundary is the bold line dividing the two classes, and as you may already know, there is a set of input examples on both sides of the decision boundary that are closest to the boundary, and these are called the support vectors, shown here as Z1, Z2, Z3, and Z4. Now, the decision function f of x takes an input example and computes a number which, if positive, classifies the example as positive, and if negative, as negative. It turns out that this decision function is dependent on something called a kernel function. The kernel function, shown here as k of z of I comma x, essentially finds out the similarity between the input example and support vector z of I. And how is this similarity calculated? Most commonly by taking a dot product between the 2 points, and we will get into the details of this for genomic sequences in the next slide. Getting back to the decision function, the decision function f of x is nothing more than the weighted sum of the similarity scores of the input example, with each support vector, plus a bias. And the weights, shown here as alpha I times yi, are the final weights assigned by the SVM to each support vector after training. So the essential takeaway from this slide is the understanding that the decision function of an SVM is significantly affected by the kernel function used to compute the similarity score between the input example and the support vectors. In this slide, I'll cover the gapped-Kamer kernel function for genomic sequences. So, like I said in the previous slide, the key goal here is to find a kernel function that computes the similarity between an input point and a support vector. In the case of genomic sequences, the input point and support vectors are nothing more than genomic sequences, and we need to find a way to get the similarity between two genomic sequences. One way to compute the similarity score is to find out how many subsequences they have in common. And that is the idea behind the gapped-Kamer kernel, which essentially generates a set of subsequences of a fixed size and finds out how many of each there is in any given sequence. yielding a feature vector that characterizes the genomic sequence. This is best explained by an example. Here, we have a sequence that we want to represent as a gapped Kamer feature vector. So first, we enumerate the possible set of subsequences. The subsequences are called Elmers, where L is the length of the subsequence. In order to get approximate subsequence matches, we allow for gaps in the subsequences, where the gaps indicate permissibility of a mismatch. Elmers with gaps are called gapped Kamers, or GKamers, where K is the number of non-gap positions, or those where we want exact matches. So in this example, we have chosen to use gap Kamers with L equal to 4 and K equal to 3. Now here, we actually tried to get the GKamer count for AGC blank. We do this by simply sliding it across the sequence and counting up the number of matches. Here we get a count of 2 for this GKamer. Proceeding in this way, we can represent the genomic sequence as a GKamer feature vector, represented as FSGKM, or the GKM feature vector for sequence S. And now, using the GKamer feature vectors of the input sequence and the support vector sequence, we can easily compute the GKM kernel function by performing a dot product of the normalized GKM feature vectors, as shown here in this equation. In this way, we can now compute similarity scores for genomic sequences. However, there is one small wrinkle. The number of possible GKamers explodes exponentially with increasing L, leading to very large feature vectors, which slows down SVM performance significantly, as really large dot products need to be computed. The optimization for that is what I'll talk about in the next slide. So in order to efficiently evaluate the GKM kernel function, it is important to observe that when we choose large GKamers, a lot of the feature vector elements of either sequence may actually be 0, since there may be no GKamers of that type in the sequence. And since we are computing a dot product, the contribution from those elements will be 0. So while calculating the dot product, we can limit ourselves only to the GKamers that are present in both sequences. Using this fact allows us to translate the dot product of two feature vectors into this alternate formula shown here, which says that the dot product is equivalent to performing a summation of common GKamers across all pairs of Elmers in the two sequences. Using this alternate formula significantly reduces the complexity of the dot product calculation. The number of common GKamers of a pair of Elmers is given by L minus M choose K, where M is the number of mismatched positions in the two Elmers. Again, this is best understood using an example. So here we have two sequences S1 and S2, for which we want to compute the kernel function, or dot product. We choose to do so with GKamers with L equal to 4 and K, or the non-gap positions, as 2. Essentially, the summation boils down to going through all possible pairs of Elmers, one from each sequence. Here, we show as an example one pair of Elmers, U1 from sequence S1 and U2 from sequence S2. Now, the two Elmers GCTT and GCTA have 3 matching positions and 1 mismatch, so M is 1. Based on this, the number of common GKamers, or H of Fm of U1 S1, comma U2 S2, must be H of 1, which turns out to be 3. And as shown here, there are in fact only 3 common GKamers which match GCTT and GTA. In this slide, I'll talk about other commonly used SVM kernels used for genome sequence classification. The first is the weighted GKamer kernel, which is simply a generalization of the GKamer kernel. Here, we assign weights to Elmers based on their position in the sequence, and correspondingly, the dot product formula gets changed as shown, and the contribution for a pair of Elmers gets scaled by the product of the Elmer weights. We will primarily use this kernel, the WGKM kernel, from here on, as it is a generalized form and reduces to the GKM kernel when the Elmer weights are set to 1. The second one, the RBF GKmer kernel, is more interesting. By mapping the GKM feature vectors to a higher dimensional space, and then performing the dot product in that space, the RBF kernel is able to capture nonlinear interactions between sequences, which, in effect, allows it to classify more complex genomic patterns than the WGKM kernel. And this kernel, called the GKM RBF kernel, has the following kernel function. Notice that it is still computed using the original GKmer kernel function, shown here. And the third one is simply a weighted generalization of the GKM RBF kernel, and as expected, assumes a weight for each Elmer in the sequence. So at this point, the 3 kinds of kernels commonly used to classify genomic sequences using SVMs should be clear. Now I'll put aside genomic sequences and kernels for a bit and talk about the integrated gradients method for decision function attribution. The goal here is, given a function in high dimensional space, as we walk from one point in that space, given by a feature vector, to another, how do we attribute the change in the function to the various dimensions? The integrated gradients algorithm does just that, and is represented by this integral here. Here, path integrated gradients pi comma I is the contribution of dimension I. F is the decision function that is being attributed. Pi mathematically represents the path traveled between the points, and beta is the normalized distance traveled on the path. The main idea of the integrated gradients algorithm is best understood by this visualization here. Here we show an incremental path element, d beta, along which we are traveling. Assume the decision function at the beginning of the path element is 0. At the end of the path element, it is f of pi of beta plus d beta. If we just travel along the dimension 1 projection of the path, d pi 1 beta, we see a contribution to f amounting to what is shown in red. If we just travel along the dimension 2 projection, the contribution is what is shown in green. The total value can be seen as the sum of contributions of the 2 dimensions 1 and 2. And this is the key observation and calculation of the integrated gradients algorithm. That is, to accumulate the local dimension-specific contributions as we walk along the path. Mathematically, it is computed by integrating dimension-specific partial derivatives of the decision function along the traveled path. So now, with this, the background description is complete, and we are ready for explaining SVM decision function attribution using integrated gradients in the following video.